In this video, we're going to look at the chain rule, and I really do like the chain rule. I like it better than product rule and quotient rule. So the chain rule is how we're going to take derivatives of composite functions. So the derivative with respect to x of f of g of x. And a lot of times when people see this, they oftentimes think, well, can't I just take the derivative of the outer function and the derivative of the inner function? And the answer to that question is no. I'll show why with a brief example down here. What the chain rule actually is the following. I take the derivative of the outer function, so I have f prime, but I leave the inner function the same, and I multiply that by the derivative of the inner function. So this seems pretty clear, or should be, for two functions, but realize that I can have sort of 3 links in the chain, 4 links. I can have many functions composed into each other. And I just follow this through, taking the derivative of the outermost function first and then working my way in. Now, we can see that this is correct, that is incorrect with a quick example. So, what if we considered the derivative with respect to x of x to the third to the fifth? And through algebra, I know that x to the third to the fifth is x to the 15th. And using my power rule, that's going to be 15x to the 14th. If I tried this not good way, this incorrect way of taking this derivative, I might think, okay, can't I just do on the outside of to the 5th power, so I'll have 5 times something to the 4th power, and on the inside I have x cubed, so I can have 3x squared. If I do 3x squared to the 4th, well, 3 to the 4th is 81. X squared to the 4th is x to the 8th. I still have a 5 times this. 5 times 81 is 405. And you can see, no, this isn't the same as that. Clearly, this is not correct. But if I follow this rule, I take the derivative of the outer function, so 5 times something to the 4th, and I leave the inner function unchanged. And then I do times the derivative of the inner function, which is 3x squared. Well, now, x cubed to the 4th is x to the 12th. I have 5x to the 12th times 3x squared. 5 times 3 is 15. X to the 12th times x squared is x to the 14th. And that one does work out. All right. A quick proof. Now, there's going to be some issue with this proof. I'll try to make it clear. I'm not going to spend too long on it. If you don't want to see the proof at all, feel free to look in the description. There will be a time where you can skip into the next 2 examples. But let's get started. So I'm going to start my proof with the left-hand side. The derivative with respect to x of f of g of x, which will be the limit as h approaches 0 of f of g of x plus h minus f of g of x all over h. And in this one, it's tricky, even trickier, let's say, than the product and quotient rule to see what to do. It's not as clear as the sum of difference formula. I can't just group up and be done. And I might not see where to go from this. But here's what I'm going to do. I'm going to multiply in another term, or another fraction. And that fraction is going to be g of x plus h minus g of x all over g of x plus h minus g of x. Now, the issues with this come from the fact that this may actually equal 0 over 0 for some domain around h approaching 0. And so there are problems with this proof. To account for those, I need more space than I have. So I'm going to go with it, but just know that there are issues with this proof I'm giving you. All right, if I sort of reorder this stuff, so limit as h approaches 0, and I will have f of g of x plus h minus f of g of x all over this part, g of x plus h minus g of x, times this numerator here, g of x plus h minus g of x all over h. So I can multiply this in because it's a special form of 1, dividing the same thing by itself. And I'm going to multiply straight across, and so I can consider this part over that and this part over that. And now, clearly, this portion here is just going to be g prime of x. What about this portion? Well, this is just a special case of the difference quotient. And it should make sense, so long as these functions are differentiable, that as h approaches 0, so as h approaches 0, g of x plus h approaches g of x. And so this is actually a special form of the difference quotient where we will get f prime of g of x. And there we have it. Now, again, I have to put some more stuff in here to account for everything. I should probably have a better explanation of this, but for the purposes of this video, for how much space I have, this should give a good idea of how I could actually construct a rigorous proof of chain rule. So let's see a couple of examples. The first example is this. Now, note, I could try to use algebra, and let's say if this up here were a 2, a squared, I would recommend just doing 2x squared minus 3x plus 4 times 2x squared minus 3x plus 4 and then doing the derivative instead of chain rule. But to the 9th power, I'm not going to multiply this by itself 9 times. So what I'll do instead is this. I'll consider the two functions. The outer function, now I don't actually write this stuff when I'm doing it, but it can help explain what I'm doing for people that are struggling here. Outer function here is u to the 9th. The inner function is 2x squared minus 3x plus 4. And in my chain rule, I need to have some derivatives here, so the derivative of f is 9u to the 8th. The derivative of g is 4x minus 3. And so I just follow through and say, okay, well, I do the derivative of the outer function, so that's 9 times something to the 8th, with the inner function unchanged, 2x squared minus 3x plus 4. I multiply that by the derivative of the inner function, which is 4x minus 3. And in here, I guess I just sort of leave it here. I could try to pull this to the front, or I could distribute the 9 into this. There's no, in this case, best answer. There are many that I think are equally reduced. I definitely would not want to expand this out to the 8th power. So this is why I like chain rule so much, is it's really quick. When you get it, you can get there right away. But what if I have more than 2 links in the chain? What about this? So in here, I actually have 3 different functions going on. I have the outer function, so I'll have that be f of u, which will be cosine of u. Inside of that, I have a square root function, so I'll say that is g of t is the square root of t. And inside the square root, I have, oh wait, let me go back because I used a t. Sorry, let's do g of v. No, I used that. Let's do g of w. Okay, lovely. Is the square root of w. And inside of that, I have h of t, which is t squared minus 9. And so I can see that, all right, the derivative of f will be negative sine of u. The derivative of g will be 1 over 2 root w. And the derivative of h will be 2t. And so I can just go through the process and say, okay, the outer function was cosine, so v prime of t. I take the derivative of the cosine, negative sine, and leave everything inside unchanged. And then I take the derivative of the next inner function, which is the square root. So that'll give me 1 over 2 root, but I leave what's inside the root unchanged. And then I take the derivative of the innermost function in this case, t squared minus 9, which will just be 2t. And I can clean this up a little bit by sending these to the numerator and canceling out these 2's. So I'll end up with negative t sine of root t squared minus 9 all over root t squared minus 9. And I actually want this evaluated at 5, so v prime of 5 will equal negative 5 sine of the square root of 5 squared minus 9 all over the square root of 5 squared minus 9, which will be negative 5. 5 squared is 25, minus 9 is 16, the square root of 16 is 4, so negative 5 sine of 4, all over 5 squared is 25, minus 9 is 16, square root of 16 is 4. And that is what we get. Alright, I hope this helped you out. Feel free to comment below if you have any questions.